Okay, so nitriles. We know how to make them now. They're kind of useful in organic chemistry because they are a way to add an extra carbon to something, right? If we had our halogen right here where this carbon is, since we add Cn minus to that, that technically homologates the carbon chain an additional carbon, which can be pretty useful. And at that point, having that nitrile, we can pretty much do whatever we want with it because we can transform it into all the other carboxylic acid derivatives through different sequential reactions. But it turns out that they can be hydrolyzed. And what do we mean by hydrolysis again? We mean that we're adding water to that molecule, and they can be hydrolyzed under acidic or basic conditions. So what do they turn into? We're going to go through the mechanisms of both the acidic and the basic conditions in a moment. But really simply, this carbon here is going to have the OH whatever added to that. And we're essentially going to turn this nitrile into a carboxylic acid. So under acidic conditions, that would be the protonated carboxylic acid, so the normal carboxylic acid. Under basic conditions, right, if we have a carboxylic acid but it's treated with base, it's no longer going to be a carboxylic acid, it's going to be the deprotonated carboxylic acid, the carboxylate. So basic conditions makes the same thing, it's just deprotonated in that case. So now we're going to show how that works under basic conditions. Okay, so how are these nitriles converted to carboxylates under basic conditions? So it'd probably be a good idea for you to pause the video here and try to work through this mechanism on your own. You should be able to think mechanistically at this point in the course, so hopefully you're not fully reliant on seeing it and memorizing it. So at least get started, draw a few of the things out that you would expect to happen, and then come back. Okay, you did that. Maybe you got the whole way through. That'd be great. But if not, what's going to happen here? Well, we have our negative nucleophile here. We have the partial positive on that carbon there. So the first step would be that negative adding to that carbon to generate the new carbon-oxygen bond and the N- species. How basic is this N- species, right? We know that nitrogens, if they're negatively charged, that means they're really basic. They really want to grab a proton. So the next thing that's going to happen is we're going to get that proton transfer from a molecule of water. That's the most acidic thing we have in solution. So that would protonate. And I'm actually going to change this. It's not really an equilibrium step at all. It's really a forward direction step. Why is that? Well, let's look at our pKa differences. Water 15.7. Once we protonate, we're going to make the NH molecule. And what's that going to be most similar to? That's most similar to NH3, which has a pKa of 38. So why is this just a single directional arrow? Because this is so much more acidic than that it's going to protonate and it will no longer be able to transfer that proton back. So what happens next then? Well, we still do have a lot of OH minus around. And what is there to deprotonate on this molecule here? Okay, hopefully you've chosen that. The most acidic proton would be this OH. How acidic is it? Is this pKa, is it greater than or less than 16? What do you guys think? Draw something out to rationalize it for yourself. So is it more or less acidic than a standard alcohol? Okay, you've done that. It's more acidic than a standard alcohol, right? Why is that? Well, if we deprotonate it, and this one is more of an equilibrium. It still is pushed in this direction. This is more acidic than what the conjugate acid's going to be. But But why is that? Why is this a favored reaction? Well, this negative charge is fully just on that one oxygen species. This negative charge on that oxygen is delocalized. Where is it delocalized to? We can draw a secondary, pretty good resonance structure where we show that the negative charge is shared between the oxygen and the nitrogen atom. That negative charge being delocalized between those two positions, we also made our water molecule here. Grab that, so we have the water molecule here. This negative charge being delocalized between two atoms means that it is more stable than it being fully on a single oxygen atom. So this is favorable in the forward direction, but just to a minor extent. What else can happen here? Again, this nitrogen doesn't want to have that negative charge. It really wants to protonate. We have more water molecules around. In fact, we just made one there. So we can get another proton transfer. That would be a single directional arrow to make us the amide. So we have an amide here. So we've shown how if we treat nitrile with base and water, we're essentially converting the nitrile to an amide. How do we get from the amide to the carboxylate? Well, we just talked about that. We learned previously earlier in the chapter that amides under basic conditions will hydrolyze, given enough time, given enough excess base and water around, they will hydrolyze to the carboxylate. So if you're having a hard time with these last few steps, I'm going to draw multiple arrows, and we'll even write earlier in notes this amide to carboxylate is going to occur under these same conditions. So the nitrile initially gets transformed to the amide, and then that gets hydrolyzed to the carboxylate under these conditions. So hopefully all these steps kind of made sense. I'd kind of recommend you writing that mechanism out, putting A, B, C for all the different steps of that mechanism, with the A being saying something like, oh, the partially negative OH was attracted to the partially positive carbon molecule of the nitrile. That's why they added to each other. Oh, why did this step happen? Oh, well, water was way more acidic than the conjugate acid, so this is just a standard acid-base reaction, and it's going downhill, et cetera, for the extra steps. That being said, let's now look at the acid-catalyzed nitrile hydrolysis. All right, so what about acid-mediated hydrolysis of nitriles to carboxylic acids? How's this one going to work? Water, is that a strong or a weak nucleophile? Yeah, we learned way back in chapter 7 that that's a weak nucleophile. That being said, weak nucleophiles don't add to electrophiles that aren't very strong. So how is this water going to add to that position? This has to somehow become a stronger electrophile, something with a larger partial positive than the initial partial positive on that carbon there. How does that happen? Well, we have acid around, right? H3O+. Anytime we see H+, that's kind of shorthand for H3O+. And that is going to protonate anything that is somewhat basic. Nitrogens are basic. They have that lone pair. So mix these two together. It's not, it is an equilibrium, but we will have some amount of the conjugate acid that we're showing here forming, and we have lots of water around. That conjugate acid, this nitrogen being positively charged, means that it is going to pull the electron density toward it. It doesn't want to have a full positive charge on it. It's going to ask for the carbon next door to lend some of its electron density to it, and it can do that. And we could even show, if we wanted to, a resonance structure showing that that positive charge is delocalized between that nitrogen and that carbon. We're not going to do that, but we could if we wanted to, and that makes that carbon more electrophilic, which makes water, a weak nucleophile, strong enough to add to that position. So that's how we get our carbon-oxygen bond form, which provides the new carbon-oxygen bond there. This is going to be really acidic. We would, if there's something moderately basic in solution, it's going to pull that proton off. Water could do that. Again, an equilibrium reaction. And at this point, what I want you guys to think about is this is essentially really similar to like a keto-enol tautomerization. We know that CO pi bonds are some of the strongest types of pi bonds. And right here we have a CO sigma bond and a CN pi bond, but the CO pi bond would be stronger. So this is essentially going to tautomerize to the amide, which will then be hydrolyzed under these acidic conditions. How would we see that? Well, we have acid around, H3O plus. This nitrogen can protonate from that acid. That would give us, and actually I showed it from that lone pair, but this nitrogen can actually do it from the pi bond, which would give us the NH2, positive charge right there, adjacent to that oxygen. At that point, we know that water can again deprotonate, and that would allow those electrons there to be used for the new pi bond, which again generates our amide that we talked about a moment ago. And that amide under acidic aqueous conditions will, and we'll draw a couple arrows again here, will hydrolyze to that carboxylic acid. Again, it probably makes sense for you to work through this part of the mechanism by yourself to remind yourself how all these little proton transfers and water addition to that carbonyl allow for that to occur. But again, if you're having a hard time doing that, I'd look back in your notes a little bit. So that is how we hydrolyze nitriles under acidic conditions.